Hello everyone and welcome. Today we are kicking off a new series where we'll explore the fundamental building blocks of deep learning. We're starting with Chapter 1, Inference, the process of how a machine takes an input and make a decision or reach a conclusion. At its simplest level, think of inference as a box. This box is designed to take a specific piece of input and, based on its internal mechanism, produce a meaningful output. It's the moment when raw data is transformed into an answer. Let's look on a few examples to see this in action. Imagine we feed this image of a cat into our box. The system processes the visual data to ask a specific question. What animal is in this image? When the box identifies the features and successfully outputs the label cat, that entire transition from image to label is what we call inference. Inference applies to text as well. If we provide the input, the sun rises in the mechanism inside the box analyzes the context and determines the most likely conclusion, morning. Whether the data is an image or a sentence, the underlying principle of deducing an output remains the same. So, to put it simply, inference is the action phase. It is the process of taking real-world data and generate meaningful output as prediction, estimations, or other decisions. In this chapter, we are going to take a high-level look on what happened inside that box. One of the most common tasks in inference is regression, the prediction of continuous value. For example, let's say we want to predict a future price of a stock. Suppose we have this stock price data plotted on a graph. We now use this box in order to make a prediction. If we feed the box historical stock prices, current market sentiment, and recent earnings reports, the mechanism uses that data to estimate a specific number, like a future stock price. Another major task is classification, where we predict a categorical value. Instead of a continuous value, the box chooses from a set of predefined labels. A classic example is digit recognition. We provide a handwritten 1 and the box identifies which category it belongs to. We've seen what inference looks like from the outside. Data goes in and a decision comes out. But how does this actually happen? What is the logic inside the box? To understand this, we need to look at the different ways a system can process information. Let's start by looking at one of the most traditional methods, analytic inference. In analytic inference, the box relies on predefined mathematical rules and formulas. For instance, if we want to find the edges of this cat, we don't need the box to learn what a cat is. Instead, we use specific equations to calculate changes in pixel intensity. The box isn't guessing, it is performing a direct calculated transformation to reach the output. While analytic inference uses formulas, statistical inference uses data distributions. Instead of a hard rule, we are looking where the data lives in a mathematical space. We represent categories as probability distributions, basically clusters that tell us where a certain type of data is most likely to be found. In this world, inference is about placement. A clear image of a cat will fall right into the heart of the cat distribution. A dog falls into the dog distribution. But what about a mixed or blurry image? It falls into the intersection, a zone of uncertainty where the system struggles to decide which category is the most likely. Let's see how the box handles this. When we feed it this cat, the internal mechanism maps the image features to its known distributions. Because the image aligns perfectly with the cat cluster, the box confidently outputs the result, cat. This is statistical inference working as intended. However, statistical inference isn't perfect. If we provide an image of a small dog that shares many visual features with a cat, the mechanism might map it to the wrong distribution. It sees the small size and the fur, moves it to the center of the cat cluster, and incorrectly outputs cat. This highlights a key challenge. The inference is only as good as the distributions we have defined. To solve the problem of uncertainty, the system establishes a decision boundary. By identifying the centroids, the mathematical center points of our distributions, we can draw a line where the distance to both centers is exactly equal. This line effectively divides our world into two territories. Now, the logic is simple. Any piece of data that falls on the left side of the boundary is classified as a cat, and anything on the right is a dog. This boundary is the rule that dictates the final output of our inference box. Now we can see exactly why our box made that mistake earlier. When we plot the features of the small dog, it physically lands inside the cat territory. Because the decision boundary is a simple, fixed line based on those distributions, the system has no choice but to follow the rule. If it's on this side of the line, it's a cat. This visualizes a fundamental limitation. If our logic or our distributions aren't nuanced enough, the inference will be confidently but objectively wrong.
In the next chapter, we will discuss on learning, how we can find these kinds of distributions and how these model boxes are created.